Hi guys, today is April 2nd and we're going to do testing convergence at endpoints and it's day 2. A couple, one of the things we need to talk about again is this alternating series test, okay? It's useful for a lot of times for the convergence at an endpoint, okay? When we've already just established the convergence by using the ratio test, okay? Um, and so we also then the ratio test also helps us to determine the interval on which it converges. All right. So again, we have to make sure that that each term of the series is positive. We have to show that the a sub n plus 1 term is less than or equal to a sub n for all n greater than or equal to some integer n. Okay. And so this could be, a lot of times it's 1, but it can be like 2, 3, 4. Okay, so like it's not smaller for the first 3 terms, but all the terms after that they're smaller. Okay, and then we also have to establish or show that the limit as n approaches infinity of the nth term is equal to 0. Okay, and if we do that, then we know it converges. Okay. And again, the geometric series test and the ratio test are probably the most important tests because they tell you the interval of convergence. The alternating series test just says, yeah, it converges. Doesn't tell us where though, okay? And then the next thing I want to talk about in sliding it up is this alternating series error bound. We've done this before, okay? If you've already used the alternating series test and you've shown that it's converging by that test, then you also know that there's an error, okay? So if we have the function minus the Taylor polynomial the nth sorry nth term polynomial, okay, the difference between those would be our error, okay, and that's r sub n of x, and that always has to be less than or equal to the a sub n plus 1 term. Now this is only true for the alternating series, okay? All right, so we have to find the error. We know the error is going to be less than whatever this term value is right here, okay? All right, so let's do some examples, okay? Let's go. All right, for example 1, we want to determine whether the series converges absolutely, converges conditionally, or it diverges, okay? And remember, if it converges absolutely, then it converges conditionally, okay? So we got to establish if it does, we want to start by testing for absolute convergence, okay? And if that doesn't work, then we switch over to the conditional convergence, okay? All right, so here we go. All right, so to check for absolute convergence, we have to take the absolute value of the term here, okay? So we're going to take sigma n equals 1 to infinity of the absolute value of -1 to the n plus 1 over n. Okay, now because we're taking the absolute value of it, remember this is going to cause it to be an alternating series, so every other term is going to be a negative term, right? So when we take the absolute value of it, they're not going to be negative, they're all going to be positive. So we can rewrite this as sigma n equals 1 to infinity of, and this is going to become just 1 over n, okay? And then we know, okay, this is the harmonic series, right? Because n equals 1, 2, 3, right? We're adding these 1 over 1 plus 1 over 2 plus 1 over 3. That's the harmonic series. We know that that diverges, okay? All right? So this diverges because sigma n equals 1 to infinity, 1 over n is the harmonic series which diverges. So what we know is that this series is not absolutely convergent. Okay, so I'm going to write that. So sigma n equals 1 to infinity of -1 to the n plus 1 over n is not absolutely convergent. Or you could also say does not converge absolutely, okay? Is not absolutely convergent. Okay, so now we're going to switch over to the conditional convergence, okay? So now we're going to look at the actual series. So sigma n equals 1 to infinity of -1 to the n plus 1 over n, okay? And okay, so when let's take a look, I'm going to look at a few terms of this series, okay? So we know when we put 1 in, right? That's going to be 1 plus 1, which is 2. That's going to be 1 over 1, which would be 1, okay? And then when we put 2 in, that'd make this 3, which is going to make it negative. So -1 over 2. So minus 1 over 2. And then we put 3 in because this will be the third term, right? 3 plus 1 is 4. So that's going to be positive. So it'd be 1 over 3. So plus 1 over 3. And so this is 1 minus 1 half plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus dot, 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 right? Okay. All right. So it's an alternating series, right? Okay. So let's establish, does this converge or not? And we have to use the alternating series test since it's an alternating series. Okay. So what's a sub n? So a sub n is the term without the piece that's causing it to alternate. Okay. So this, in this case, it'd be 1 over n. Okay. And what do we know about 1 over n? Well, that's for n bigger than 1, right? Then that's going to be always positive, which is what we have to show, right? So this is greater than 0. Okay. So what we're showing is a sub n is greater than 0. The values are all positive. Okay. And then we have to show that 1 over n plus 1 would have to be less than or equal to the a sub n term, right? 1 over n. Well, yes, this is going to be smaller because this denominator is bigger than this denominator. Okay, so now we've established that a sub n plus 1 is less than or equal to a sub n, right? Okay, and then we have to do the third one is take the limit as n approaches infinity of 1 over n. Okay, well, this denominator is getting bigger and bigger and bigger. The fraction approaches 0. So this is equal to 0. So we've established the third piece, which is the limit as n approaches infinity, a sub n is equal to 0. So we've established these three things, right? Okay, so what does that tell us? That tells us that this converges, right? So sigma n equals 1 to infinity of -1 to the n plus 1 over n converges. And we know it converges by, and we have to state this, we have to state what test we're using, the alternating series test. Okay, so it wasn't absolutely convergent, but the series without taking the absolute value of it is convergent, right? So that means it's conditionally convergent. So we would say that, okay, so sigma n equals 1 to infinity of -1 to the n plus 1 over n is, or converge, we could say converges conditionally. Or we could say the series is conditionally convergent. Okay, we could say it two different ways of saying the same thing. Okay, and both are correct. All right. Now we want to find the bound for the truncation error after 99 terms, right? Okay, so that's our, since it's an alternating series, we can find the error after the after 99 terms. Okay, so this would be r sub 99, right? We're going to use 99 terms, right? So r sub 99 of x. And what do we know about that? That's going to have to be less than or equal to a sub 100, okay? I'm going to slide this up a little bit. Okay, so what this means is that the error, r sub 99 of x, has to be less than or equal to, okay, a sub 100. Okay, a sub 100 is the a sub n from up here, right, which is 1 over n. So this would be 1 over 100. Okay, so that means our error for our Taylor polynomial approximation, if we go out 99 terms, then we know that our error is going to be less than or equal to 0.01, because that's 1/100th. Okay, so we are pretty close to being accurate to the actual function. Okay, all right, so that's the error bound. Okay, for the 99 terms. All right, let's go to example number 2. Same instructions as example 1, but we're looking at a different series this time. Okay, so we want to check for the absolute convergence of the series, or is it converge absolutely, does it converge conditionally, or does it diverge? Okay, so once again, we're going to start out by doing the absolute convergence of it, checking for that. Okay, so we know that sigma n equals 1 to infinity of the absolute value of -1 to the n over the square root of n. The absolute value of this would give you sigma n equals 1 to infinity, and this would become just 1 over the square root of n. Now this is the power of 1/2, right? So I'm going to change this. This is sigma n equals 1 to infinity of 1 over n to the 1/2 power. Okay, now this is a p series, right? And our power is 1/2. Okay, and if our power is between 0 and 1, including 1, then we know it diverges. So we automatically know that this series diverges by the p series test. Because RP is equal to 1/2, and we know 0 is less than P less than or equal to 1, it's going to diverge. Okay, all right, so we know it diverges. Okay, so which means our original series does not converge absolutely. Okay, so I'm going to write it that way, a little bit different than we did last time. So n equals 1 to infinity of -1 to the n over the square root of n does not converge absolutely. So the next question we have to ask is, does it converge conditionally? Okay, so now let's look at this, the original series, right? Sigma n equals 1 to infinity of -1 to the n over the square root of n, right? Okay, which could be written as sigma n equals 1 to infinity of -1 to the n times 1 over n to the 1/2 power. Okay, or square root of n. Okay, so from this we can tell our a sub n is this, right? A sub n is equal to 1 over the square root of n, which is also 1 over n to the 1/2 power. Okay, all right, and it's alternating because we have -1 to the n. So we're going to go to using the alternating series test. All right, so we know a sub n is this. Okay, so we have to establish, is a sub n, okay, actually let me rewrite this. Let's just write 1 over the square root of n. Okay, 1 over the square root of n, that is greater than 0. Okay, because n is going to be positive, right? Because n is 1, 2, 3, 4, 5, and so on, right? So yeah, this denominator is going to be positive, which makes the fraction positive. Yeah, so we're showing that a sub n is always going to be greater than 0. Okay, all right, so what about 1 over the square root of n plus 1? Is that less than or equal to 1 over the square root of n? Well, the square root of n plus 1 is going to be bigger than the square root of n. And because that's in the denominator, this fraction is going to be smaller than this fraction always, right? So we've established that a sub n plus 1 is less than or equal to a sub n. And then we also have to do the limit as n goes to infinity of 1 over the square root of n. That's going to go to 0, right? Because that just denominator keeps getting bigger and bigger and bigger, okay? So what do we know? We know this series now converges by the alternating series test. So sigma n equals 1 to infinity of negative 1 to the n over the square root of n converges by the alternating series test, which means sigma n equals 1 to infinity of negative 1 to the n over the square root of n converges conditionally. Or is conditionally convergent, okay? All right. Okay, so then the next thing we gotta do is the truncation, right? Okay, so we know we're going 99 terms again. So the error r sub 99 of x has to be less than or equal to a sub n plus 1. So this is 99, so this is gonna be 100, okay? So that means our error is less than or equal to 1 over, and this would be the square root of 100. Well, that'd be 10, right? So r sub 90, the absolute value of r sub 99 of x is less than or equal to 1 over 10. Okay, so for this series, our error, if we go out 99 terms, is less than or equal to 0.1. Okay, and that's what our error would be based on that alternating series error bound. Okay, this is the biggest error we could have, right? All right, because our error, this is our error right here. It has to be less than this number right here, okay, or equal to it. Okay, all right, so this is the upper bound of it. Okay, all right, let's go to example number 3. All right, so for example number 3, what I want us to be able to do is find the interval of convergence of the series, okay? And then for what values of x does the series converge absolutely and conditionally, okay? All right, so here we go. All right, if we look at this, we're gonna put 0 in here for n, right? So I'm gonna write out the first few terms of the series, okay? So if we put 0 in here, that'd be x plus 5 to the 0 power, right? And this would be equal to 1, okay? It wouldn't be 1 if x was negative 5, okay? But then we're gonna talk about that later. That's the center of convergence, okay? So it will always converge at x equals negative 5, okay? So this would be 1, and then we're gonna put 1 in, right? So that'd be plus, and then x plus 5, and then we're gonna put 2 in, right? And that'd be plus x plus 5 squared, and then plus, and then we're going to put 3 in, right? 0, 0, 1, 2, and then 3, and that'd be x plus 5 cubed, right? Plus, and then dot, dot, dot. We're just going to continue this, okay? Now, if you notice what this is, it's a geometric series, right? So the series is a geometric series. And our r is equal to x plus 5, because that's what we're multiplying by each time, okay? So we can check for the absolute convergence of this, but we should already know, okay, that it converges absolutely when our r is less than 1. And it's going to diverge when our r, the absolute value of r, which is the absolute value of x plus 5, is greater than or equal to 1, okay? So we're going to check the absolute convergence of this, okay? So here we go. So sigma n equals 0 to infinity, absolute value of parenthesis x plus 5 to the n. Okay, now when you take the absolute value of something like this, okay, this n is going to be positive, right? So we can actually bring this out and we can rewrite these as sigma n equals 0 to infinity of the absolute value of x plus 5 raised to the n power. Okay, that will always be true. Okay, so we're checking for the absolute convergence of this. Okay, so we know that it converges absolutely when the absolute value of x plus 5 is less than 1. We know the series converges absolutely. We also know because it's a geometric series that when the absolute value of x plus 5, okay, is greater than or equal to 1, it diverges. So we automatically know, okay, it's converging for these x values, and it's converging absolutely, and it's diverging for these. So there's no conditional convergence. It won't happen on geometric series, okay? Okay, so for this, okay, we can tell that our radius of convergence is 1 right here, okay? All right, so what's going to happen is that this x plus 5 has to be between -1 and 1. So -1 less than x plus 5 is less than 1. I'm just solving this absolute value inequality, okay? And then I'm going to subtract 5 from the left, the middle, and the right. So that would give me -6 is less than x is less than -4. Okay. So right here, this when you get the absolute value by itself like this is our radius of convergence, okay? You could also get it, and I showed you this earlier, is you could subtract these and find the distance and divide by 2. So this is a distance of 2, right? From -6 to -4. That's a distance of 2. Half it is 1, okay? That's this right here too, all right? So we know, I know I didn't ask this, okay? But what is the radius of convergence? The radius of convergence is 1, okay? The interval of convergence okay, is between -6 and -4, not including, right? Now, on some of these, when they're not geometric series, we're going to need to check the endpoints, -6 and -4. That's what this lesson's all about, okay? We're going to need to check, and I'm going to show you how to do that in a few minutes, okay? But this is the interval of convergence. We know any x value outside of this will cause it to be divergent, okay? So we know for sure because of this. Oh, I didn't write the 1 here. Okay, I should have written 1 there. Okay, so for all of these x values, it's absolutely convergent. For all of these x values, it's divergent. So we figured it out for all the x values. It's either absolutely converging or it's diverging, okay? So this is the interval of convergence, okay? And then it converges absolutely on, and it would be this interval, -6 to -4. For geometric series, the interval of convergence and where it converges absolutely are going to be the same thing, okay? And then the series is never conditionally convergent, okay? There are no x values on which the series is conditionally convergent or converges conditionally, okay? The series is never conditionally convergent. Okay, and this is true. This is always going to be true for every single geometric series. Okay, actually, I'm going to do that in red. Because for geometric series, it's either going to be converging absolutely or it diverges. Okay. You never have something that's in between. Okay. All right. So that is example number 3. Let's do example number 4 next. So let's turn the page. All right. So for example 4, it's same instructions as the last one. In fact, example 5 and example 6 are going to be the same instructions. Okay. We're trying to determine for what x values does this thing converge absolutely and conditionally. Okay. And find the interval of convergence. Okay. All right. So here we go on this one. Okay. So we're going to check for absolute convergence. Okay. The overall thing first. All right. All right. So this becomes sigma n equals 4 to infinity of the absolute value of n x to the n over 4 to the n times n squared plus 1. Okay, so we're checking the absolute convergence of this series. Okay, now what happens is this becomes sigma n equals 4 to infinity. This n is always going to be positive because we're starting at 4, right? Okay. And it'd be the absolute value of x sub x raised to the n power, but that would be equivalent to the absolute value of x raised to the n. So we could rewrite this as n times the absolute value of x raised to the n over, okay, 4 to the n is always going to be positive, and n squared plus 1 is always going to be positive. So we don't even need the absolute values for those. Okay, so that's what this becomes. All right, now we have powers of n, right? Okay, so since we have powers of n, and this isn't a geometric series because we have this x raised to the n, right? All right, so we need, this is what we need to use is the ratio test because this is not a geometric series. Okay, all right, so we're going to use the ratio test, which means that we're going to find the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. That's equal to the limit as n approaches infinity of, okay, so really this is going to be a product and it's the reciprocal of this one, right? So a sub n plus 1, so this would be n plus 1, let's do over here. This would be n plus 1 because I'm taking the absolute value of it, okay? So this would be n plus 1, so absolute value of n plus 1 times x raised to the n plus 1 over 4 to the n plus 1. And then I'm going to use 2 sets of parentheses here. So parenthesis and then n plus 1 squared plus 1. And then times that by, okay, a sub n, right? But it's going to be the reciprocal of a sub n. So this becomes 4 to the n times n squared plus 1 over n times x raised to the n. This absolute value right here, okay, this outside one is going to be taken care of to figure this one out, all right? So we don't have to use this one. We can go back to this because we're taking the absolute value of it. When you do the ratio test with the absolute value, you're actually checking for the absolute convergence of it, okay? All right, I wanted to point that out, all right? Okay, so here we go. So if we do this, all right, then I'm going to rearrange the terms. So this is the limit and n goes to infinity. And I'm rearranging the terms so it's more beneficial to see what's going on. So I'm going to do the n plus 1 over the n term. You wouldn't have to do this one first. And then times, and I'm going to do 4 to the n over 4 to the n plus 1. And then times, and okay, n squared plus 1, and down here, n plus 1 squared plus 1, right? yeah, n squared plus 1 over, and then n plus 1 squared plus 1. And then times there's a fourth one, right? And then it's this x to the n plus 1 over x to the n. Okay. This one doesn't simplify. We're going to have to do the limit on this one, and we're going to have to do the limit on this one. These two will simplify a little bit, okay? Now, there's this would be 4 to the n minus n minus 1. So this makes it 4 to the negative 1. And then 4 to the negative 1 is really 1 over 4. This becomes 1 over 4, all right? So this is the limit as n approaches infinity of the absolute value of n plus 1 over n times this becomes 1/4. This one is, I'm just going to leave it like this, n squared plus 1 over n plus 1 squared plus 1. And then times, and then this becomes x to the n plus 1 minus n, right? So it's just going to be x to the first or just x. Okay. So we take because of limit properties, we're going to take the limit of each one of these, right? But but those are inside absolute values. Now this is going to become 1, right? Because it's n over n. You're looking at the magnitude of it, right? So that's going to be 1 times, well, in the second one, there's no place to put the n, right? So it's just going to stay 1/4. Thinking about this, okay, the highest power on the numerator is n squared. Well, the highest power in the denominator, if we were to square this out and add 1, the highest power would still be n squared, right? So we have n squared over n squared. So that'd still be 1. And then we take the limit as n goes to infinity. Now this x is changing, right? These were all numbers, and they were positive, so we didn't need the absolute value. This one we are, because it depends on what the x is, right? So this is going to become, as n goes to infinity, it's just going to be times the absolute value of x. So this is 1 times 1/4 times 1 times the absolute value of x, or that would be equal to 1/4 times the absolute value of x. Okay, now that's the ratio test, right? Now we know from the ratio test that this is going to be absolutely convergent when this is less than 1. Okay, so we're going to write 1/4 times the absolute value of x is less than 1. We know it's going to be absolutely convergent for these. Okay, because that's what this absolute value does for us. Okay, so all right, so what does that mean? That means the absolute value of x is less than 4. Okay, so when we get down to just the absolute value of x, okay, this number right here is our radius of convergence. Okay, so our radius of convergence is 4. Okay, now our interval of convergence, we can use this to get it, right? Because when is the absolute value of x less than 4? Well, it's when negative 4 is less than x, which is less than 4, right? And so our interval of convergence is from negative 4 to 4. That's a distance of 8, and half of 8 is 4. Okay, so that's why our interval of convergence, or radius of convergence, is 4. Okay, so we can determine that. All right, now we know for sure it's absolutely convergent from negative 4 to 4. But what about at these endpoints? Is it absolutely convergent at the endpoints? Is it conditionally convergent at the endpoints? What is it? Okay. All right. So let's figure that out, and that's the next part. Okay. You probably are going to need to grab another piece of paper. Okay. These do take a little bit of time. Okay. So we're going to check now the endpoints. All right. All right, so let's do that next. I'm going to slide my paper up a little bit. Okay, and the way we check our endpoints, okay, okay, and the way we're going to check our endpoints is we're going to put in x equals 4. Okay, now our endpoints for this interval, our endpoints are -4 and 4. Okay, and right now we're not including them. Okay, all right, so that changes everything because back up here on our original series, we have an x, right? So what we do to check the endpoints is we're going to replace this x with a 4, okay? And then we're going to check the absolute convergence of that series, all right? And that's how you do it, okay? So actually what's a pain is that now we got to put x equals 4 and we get a brand new series, and we got to check that series for absolute convergence and conditional convergence at that x value. And we need to do it for x equals 4, and then we're also going to need to do it for x equals -4, okay? So this is sigma. This is where it's kind of a pain, all right? So we have n equals 4 to infinity of n, and this is where my x was, right? It was x to the n. So now this is going to be times 4, because that's my new x, right? My x is 4 for this, 4 to the n over 4 to the n times n squared plus 1. Now, what's nice about these is some of it cleans up, right? Here I have 4 to the n over 4 to the n. So this series actually becomes sigma n equals 4 to infinity of n over n squared plus 1. All right. Now, we got to check the absolute convergence of this, okay? So, sigma n equals 1, not 1, whoops, 4 to infinity of the absolute value of n over n squared plus 1. Okay, so in essence, we don't even need the absolute value because it's going to be the same thing, okay? So this is going to be equal to sigma n equals 4 to infinity of, okay, because n is always going to be 4 or bigger, right? So it's going to be positive, and this is going to be positive. So we really don't need the absolute value, okay? Okay, so it's the same series, right? Even when we take the absolute value, it's going to be the same series. So when we do this, we're going to actually be able to tell if this converges, right? Then it's going to be absolutely convergent at x equals 4. And then what we would do is include 4, okay? But if it diverges, okay, the original series would diverge and this one would diverge, right? So it wouldn't be absolute convergence, and neither would be conditionally convergent, okay? All right, so how are we going to do this? How do we test for the convergence of this? Okay, so I'm thinking that this is something like n over n squared, right? Which is really 1 over n. All right, so what I'm thinking about is I'm going to compare this to 1 over n. And I know 1 over n is the harmonic series, and I know the harmonic series diverges, right? And so I'm thinking I'm going to use the limit comparison test, okay? So my a sub n is going to be n over n squared plus 1. And my b sub n, the one I'm going to compare it to, is going to be 1 over n. Okay. And I know this one is greater than 0. And I also know this one is greater than 0. Okay. All right. And I know this one, the series 1 over n, will diverge because it's the harmonic series. And if I do the limit as n approaches infinity of a sub n over b sub n, okay, and we get a positive value out of this, then I know that whatever this one's doing, this one will do the same thing, okay? All right, so here we go. Let's take the limit as n goes to infinity of a sub n over b sub n. All right, so this is equivalent to n over, oh, I forgot the limit. Okay, so this is the limit as n goes to infinity of n over n squared plus 1 over 1 over n, right? Okay, so I'm going to multiply top and bottom by n over n. That would get rid of this one, right? Because I have a complex fraction. Okay, so then this would be equivalent to the limit as n approaches infinity of n squared over n squared plus 1. Well, what do we know about this? Well, as n goes to infinity, if n's going to infinity, we can just look at the magnitudes of the numerator and denominator. Well, they're the same, right? So this is just going to come out to be 1. And remember, if this comes out to be a positive value, okay, then what we know is that however, they'll behave exactly the same way. So if this one's diverging, okay, then this one also diverges. So now I have to establish this one, okay? So we also know that sigma n equals 1 to, we can go 4 because that's what this one does, okay? 4 to infinity of 1 over n diverges because it's the harmonic series. Which diverges. Okay, so therefore, this one, which is also this one, right? So sigma n equals 4 to infinity, absolute value of n over n squared plus 1, which is also equal to sigma n equals 4 to infinity n over n squared plus 1, diverges, got ahead of myself, diverges by the limit comparison test. Okay, so we now have established that at x equals 4, this series is not absolutely convergent and it's not conditionally convergent, it's actually divergent, okay? So at x equals 4, the series is divergent. Okay, which means it's not converging for this endpoint at x equals 4. Okay, what about x equals negative 4? Okay, so now we got to do that. So we've got to grab another piece of paper. Okay, so I'm going to grab another piece of paper and then I'll be back. Okay, so back at example number 4. Okay, now we're checking the endpoint. Let me slide this down just a little bit. Okay, we're going to check at x equals, we just checked x equals negative 4. Okay, now we got to check at x equals, we checked at x equals 4, sorry. And then we got to check at x equals negative 4. Okay, so that means we're going to have sigma, right? We're going to put negative 4 in for x into our original series that we're looking at. Okay, this is n equals 4 to infinity of n times negative 4, because that's where our x was, right? Raised to the n over 4 to the n times n squared plus 1. Okay, so this becomes, we're going to clean this up a little bit. This is really negative 1 times 4. So we could rewrite this series as sigma n equals 4 to infinity of n times negative 1 to the n times 4 raised to the n. That'd be equivalent to this numerator here, over 4 to the n times n squared plus 1. Okay, so 4 to the n, 4 to the n, right? Those are going to cancel, and this could be written as sigma n equals 4 to infinity of, I'm going to put the -1 to the n first. So -1 to the n times n over, and then this would be n squared plus 1. All right. So then if you look at this, okay, if we check the absolute convergence of it, okay, we're going to take the absolute value of this, okay? So we're checking for absolute convergence when I do this. So we're checking for the absolute convergence at x equals -4, all right? So sigma n equals 4 to infinity, absolute value of -1 to the n times n over n squared plus 1. Okay, so now when we take the absolute value of this, this is going to go away. We're not going to be alternating anymore, right? So this becomes sigma n equals 4 to infinity of n over n squared plus 1. Now, what did we just do? We just did this one, right? And we know it from the previous, for at x equals 4, we got this, it's the same series, right? And we know we've already established that when it's this series, that this series diverges, okay, from the previous problem, okay? All right, so we know that this one diverges by the limit comparison test, right? Okay. We don't need, I mean, if you have the same series, you don't need to go through and do the test again. All right. Okay. So now we've done this. We know what this is telling us is it's not absolutely convergent at x equals 4, x equals -4. Okay. So the series, let's write that. The series is not absolutely convergent at x equals -4, but it could still be conditionally convergent. Okay. So now we got to go and check the conditionally convergent of it. Okay. So we have sigma n equals 4 to infinity of -1 to the n times n over n squared plus 1. All right. So this is an alternating series because we have -1 to the n, right? So we go to the alternating series test, right? All right. So let me rewrite this. So this is becomes sigma n equals 4 to infinity of -1 raised to the n and then times n over n squared plus 1. So this is our a sub n, right? That's our a sub n. Okay, so this is at x equal, again, we're checking at x equals -4. Okay, so for the alternating series, we have to show that n over n squared plus 1, is that always going to be greater than or equal to 0, right? Is that greater than, or I'm sorry, just greater than 0? Is it greater than 0? Absolutely, right? So we know that this is going to be greater than 0. Okay, why? Because this is 4, 5, 6, 7, 8, right? And this is 4, 5, 6, right? These will, you're always going to have a positive over a positive for n being 4 and so on, okay? So yeah, we've established that. Okay, so now how about a sub n plus 1, right? So this would be n plus 1 over n plus 1 squared plus 1. All right, is that going to be less than or equal to n over n squared plus 1? Okay. All right, so this is going to always be, this numerator is going to be 1 more, right? And this one's going to be n squared. Actually, let's write this out. So this would be n plus 1 over, this would be n squared plus 2n plus 1 plus 1, right? Which is less than or equal to n over n squared plus 1. Okay, so this would be n plus 1 over n squared plus 2n plus 2, right? Which is less than or equal to n over n squared plus 1. Okay, so this is just adding one more to this. Okay, so we got to kind of worry about the numerator now because they're not the same, right? Okay, so this is just adding 1 to the numerator, okay? This one, okay, is adding actually 2n plus another 1 here, right? So this numerator is going to grow faster than this one, and this is going to grow even faster than this, okay, than the numerator here. So this one's always going to be smaller than this one, always. This adding 1 causes problems, okay? But we know that adding 1 to the numerator is not as doesn't have the significance as adding 2n plus 1 down here in the denominator, right? This is going to grow faster than this, okay? All right, so we know our denominator is going to be bigger, is always going to be bigger and bigger and bigger than this, okay? Another way to look at this is put this one into your calculator, put this one into your calculator, and look and take a look and see, is this one going to be, is this, when we graph them, is this one always smaller than this one? And it will be, okay? All right, so now we've shown that a sub n plus 1 is always going to be less than or equal to a sub n, all right? And then we have to do this one, the limit as n goes to infinity of n over n squared plus 1. Okay, and then, all right, so what happens when we take the limit as n goes to infinity of n over n squared plus 1? Okay, so we're really comparing n over n squared. This one's going to grow faster, so this one's also going to go to 0. So what do we know about the series? It's converging, right? Okay, so this is sigma n equals 4 to infinity of -1 to the n times n over n squared plus 1 converges by the alternating series test. Okay, which means the series is conditionally convergent at x equals -4. Okay, so the original question was, okay, for what values of x is it converging, right? Is it for what values of x does the series converge absolutely and conditionally, okay? So from the very get-go, okay, we had, and I'm going to write all these out, okay, we have the radius of convergence, okay, and let me grab my paper. Okay, so we have the radius of convergence is 4. Okay, we now have the interval of convergence. Okay, and the interval of convergence is, okay, so we have the intervals from -4 to 4, but what we just established is that it's converging conditionally at -4 and it's diverging at 4. So when we talk about the interval of convergence, we're going to include -4, but we're not going to include 4. Okay, so the interval of convergence is bracket -4 to 4. Oh, whoops, I didn't mean to put the bracket on the right. Okay, let's take that off. Whoops. All right, so let's write 4, and that should be a parenthesis, okay? Because what did we show at x equals 4? It was diverging, right? So we don't want to include 4. That would be really, really wrong, okay? Now, where is it absolutely convergent, okay? So it's absolutely convergent. on, and it was conditionally convergent at x equals -4. It was only absolutely convergent between -4 and 4. So this one's a parenthesis -4 to 4. And then we say it's conditionally convergent, and it's only one x value it's conditionally convergent at, okay? So we say it's conditionally convergent, and it's not an interval, so it's at an x value, so we're gonna write at, and it's at x equals -4. Okay. Now I know I didn't ask for the radius of convergence. I'm just throwing that in there. Okay. Really, all I asked you was the interval of convergence, absolutely convergent, and then where is it conditionally convergent? So these are the x values where this is the interval of convergence. Okay. These are the x values where it's absolutely convergent, and this is the one x value where it's conditionally convergent. Let me slide it up. Sorry about that. Okay. All right. These are long problems, okay? And I know that I've done the homework, all right? They take a while, okay? I'm going to give you many days to do this. And what I would do is just do a couple problems a day, okay? And I'm going to look at how many problems we have, and I'm going to give you probably about a week to do this, okay? Because we have AP review that we're doing too, all right? Okay? All right. So let's go to the next example. Okay, so here's another one. Okay, so we have sigma n equals 1 to infinity of -1 raised to the n plus 1 power, and then we have x to the 2n over 2n. Okay, so we're going to check absolute convergence of this. Okay, so this becomes sigma n equals 1 to infinity of the absolute value of -1 to the n plus 1, and then x to the 2n over 2n. Okay. And so this is going to go away, right? Because we're taking the absolute value of it. And this becomes sigma n equals 1 to infinity of, and this would be the absolute value of x to the 2n, which could be written as the absolute value of x raised to the 2n power, over this denominator is never going to be negative because n is starting at 1. All right. So this is just 2n. Okay. Now, what we're going to do is we're going to do, if you look, we have powers of n, right? And so what we want to do, and here's the thing, we don't have just powers of n. We have x to the 2n power, right? And then we have 2 times n, all right? So if we didn't have this right here, I would say you might be able to look at this as a geometric series, all right? But we can't on this one, all right, because we have this 2n. So what we want to go to when it's not a geometric series is you got to go to the ratio test, all right? So we're going to do the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so then what's going to happen is we really don't need to worry about this one because we're taking the absolute value of it, okay? Because that causes it to be negative and we're taking the absolute value of it. Okay, so this becomes the limit as n approaches infinity of the absolute value of, and this would be x to the 2 times n plus 1 over 2 times n plus 1, and then times, and then it's going to be the reciprocal of this, all right? So it'd be 2n over x to the 2n. All right, so this is equal to the limit as n approaches infinity of the absolute value of, this would be x to the 2n plus 2. And I'm going to put this denominator here underneath this one. So over x to the 2n, and then times, and then 2n, and this one's going to be 2n plus 2. Okay, so what happens when we take the absolute value of this? Oh, well, I'm going to actually clean this one up a little bit more, okay? So this is the limit as n goes to infinity of Okay, and this would be x squared because we have x to the 2n plus 2 minus the 2n. So that'd be x squared. So absolute value of x squared times 2n over 2n plus 2. Okay, as limit as n goes to infinity, this one's going to be absolute value of x squared times, and this is just going to be 2n over 2n, which is just going to be 1. Okay, so times 1. All right, so this is the absolute value of x squared. Now, the absolute value of x squared can also be written as the absolute value of x raised to the second power. That's going to be helpful, okay? Okay, so now, okay, when will this converge absolutely? So this is going to, whatever this is, whatever we get out of this is going to converge absolutely, okay, when the absolute value of x squared is less than 1, okay? All right, so the absolute value of x squared, okay, what you can do is you're going to be able to square root both sides, right? This is only going to happen when the absolute value of x is going to be less than 1. Okay, and then that would be the case where we have -1 is less than x, which is less than 1. Okay, so we know that when x is between -1 and 1, this is going to have to converge absolutely. Okay, all right, but now we have two endpoints, right? We have x equals -1 and x equals 1, okay? So we know it's converging absolutely in between, but we don't know if it's converging absolutely or conditionally or diverging at x equals -1 and at x equals 1. So what we have to do is go back up here to our original series and we got to check our endpoints, okay? So we're going to check our endpoints at x equals -1 and we're going to check our endpoint at x equals 1, okay? And so grab another piece of paper. All right, so we're going to check the endpoints. And that would be at x equal, I'm going to do x equals -1 first. It doesn't matter which one you do first, okay? All right, so we know that because when x is -1, this series becomes sigma n equals 1 to infinity of -1 to the n plus 1, and then times, okay, so this is where my x was, right? And it's going to be -1 raised to the 2n power over 2n. Okay. Now, what's going to happen here? Okay. So I'm multiplying my n's by 2, which is going to make this power be even. This power will always, always, always be even. And since that power is always, always, always going to be even, okay, then that's going to cause this -1 to be an even power. This is going to be 1. So what happens is this becomes sigma n equals 1 to infinity of -1 to the n plus 1 times 1 over 2n. Okay? And what we're going to do next is we're going to check the absolute convergence of this, okay? So at x equals -1, we're going to do sigma n equals 1 to infinity, the absolute value of -1 to the n plus 1 times 1 over 2n, excuse me. All right. Now, taking the absolute value of this, we take the absolute value of this times the absolute value of this. Well, that's going to make this 1, right? So this is going to become sigma n equals 1 to infinity. And then this would be just 1 over 2n. Okay. And then this becomes 1/2 times n equals 1 to infinity of 1 over n. because this is going to be 1 over 2. Each term is going to have 1 over 2 being multiplied by 1 over 2, right? And this denominator is just going to get bigger and bigger and bigger as it increases, right? That this can be, let me rephrase that, okay? This can be thought of as being 1/2 times 1 over n, all right? So each term of our series is being multiplied by 1/2, which means I could factor it out and have 1/2 times the series, right? Okay, so that means I can factor this out. Now, what do we know about this series? Well, that's the harmonic series, right? So if this is the harmonic series and I'm simply multiplying by 1/2, this diverges. So multiplying by 1/2 is also going to diverge, right? Okay, so we would say that 1/2 sigma n equals 1 to infinity of 1 over n diverges because the series sigma n equals 1 to infinity of 1 over n is the harmonic series, which diverges. Okay, so what we've established is it's not absolutely convergent at x equals -1, okay? The series is not absolutely convergent at x equals -1, okay? It could still be conditionally convergent, okay? All right, so now we gotta look at, is it conditionally convergent, okay? So sigma n equals 1 to infinity, and our series became this one, right? So it'd be -1 to the n plus 1 times 1 over 2n. Okay, so, okay, this is an alternating series. We got to use alternating series test, right? So 1 over 2n, what do we know about that? Well, 1 over 2n is greater than 0, right? And I should say this, our a sub n is 1 over 2n. Okay, so 1 over 2n is greater than 0. Okay, what if we look at a sub n plus 1? Okay, so 1 over 2 times n plus 1. Is that less than or equal to 1 over 2n? This one's going to be a little bit easier than the last one. Okay, so this would be 1 over 2n plus 2 is less than or equal to 1 over 2n. It's a lot easier when the numerators are the same to compare these, right? Okay, because they're both 2n, but this one's adding 2. So this denominator is bigger than this one, right? And because this denominator is bigger, this overall fraction is going to be smaller than this overall fraction, right? So this one's always going to be smaller than this one, okay? All right, so we've established that a sub n plus 1 is less than or equal to a sub n, all right? And then we have to look at the limit as n goes to infinity of 1 over 2n. Well, that's 0, right? That should be an automatic thing now. Okay, so what do we know? All right, so what we know is that it's conditionally, this series is convergent, right? All right, so let's say, okay, so this series n equals 1 to infinity of -1 to the n plus 1 times 1 over 2n converges by the alternating series test. Okay, so what do we know? That means the series is conditionally convergent at x equals -1. So let me slide that up. Sorry, the series is conditionally convergent at x equals -1, okay? All right, so now we got to do at x equals 1, right? Okay, so we got to do the same thing at x equals 1. I know these just take a long time because you're doing all these tests for the series, okay? All right. So what's maybe you're not seeing the big picture, okay? Okay, these series are Taylor series, right? Okay, and because they're Taylor series, we want to know where we can use these Taylor polynomials, okay, to approximate the functions, and for what x values are they converging, right? So what x values can we use to approximate this, right? And so that's what we're doing. That's why we're doing all this. We're not, because it would take even that much longer, right? We're not dovetailing in and showing like why we're doing this with the Taylor series. Okay, I wish we would. I wish we could do this whole thing, but man, you could do one problem and be like 10 pages. All right. Okay, so let's go and let's do the convergence at x equals 1 and check that endpoint. Okay, so I'm going to grab another piece of paper. All right, and I'll be back. Okay, so I have my second piece of paper here. And now I'm going to check at x equals 1. Let me slide my paper down just a little bit. So we're going to check x equals 1. All right. So that means our series becomes sigma n equals 1 to infinity. We still have that negative 1 raised to the n plus 1 power. And then we have our fraction, right? And our fraction was x to the 2n, but our x is 1. So it's going to be 1 to the 2n power over 2n. Okay. Now, what's 1 to the 2n? Well, this is just going to be 1, right? So this is going to be sigma n equals 1 to infinity of negative 1 to the n plus 1 times 1 over 2n, right? And if you look at this, okay, that's exactly what we got when x equals negative 1, right? Okay, this is the exact same series, right, as when x was negative 1. Okay, so it didn't change on us, right? So because it didn't change, we don't have to go through, this is gonna be nice, we don't have to go through all the tests again because it's the same series, right? It's just at x equals 1, it happened to give us the same series. Now, it's not always gonna happen this way, but it did for this one, right? It did work, okay? So by the previous endpoint, we know it's the same series, so the convergence will be the same as at x equals negative 1. As at. Okay, so let me fix this. So as at, same as at x equals negative 1. Don't judge my English, all right? By the previous endpoint, the convergence will be the same as at x equals negative 1. Okay, so what was it at x equals negative 1, okay? At x equals negative 1, it was conditionally convergent, okay? So what we know is that the series is conditionally convergent at x equals 1. Okay, so back to this, I'm going to grab my papers from the previous problems, okay? What's the radius of convergence? Okay, so you look at this, all right here, we can tell that the radius of convergence is 1, okay? So I'm going to write radius of convergence is 1, okay? The interval of convergence. Now, when I say convergence, it doesn't matter whether it's absolute convergence or conditionally convergence, just where it's convergent, okay? Just kind of a generic term, okay? So what we established is it was from the ratio test that it was convergent in between -1 and 1, okay? But then from the endpoint tests, all right, we determined that it was conditionally convergent at -1, and it was also convergent at x equals 1, which means the interval of convergence would be bracket -1 to 1, okay? So it's including -1 to 1, okay? Now, where's it absolutely convergent? So absolute convergence. So for what x values is it absolutely convergent? Okay, and it was at -1, it was conditionally convergent, and at 1, it was conditionally convergent. So we don't include the endpoints on this, okay? So it's absolutely convergent on the interval parenthesis -1 to 1. And then where was it conditionally convergent? So conditionally convergent at, and it's at x equals -1 and x equals 1. Those are the two x values that it's conditionally convergent on, okay? Guys, I really hope this is making sense. And this is a long lesson, and it's the last of the long lessons, all right? Other than AP reviews, sometimes those take a little bit of time too, okay? All right, so now let's turn to example 5 because we finished example 4 finally, all right? Okay, I think I just said example number 5, but really this is example 6, and this is gonna be the last example. I think you have example 7 in your notes. We're not gonna do that one. That's actually gonna be a homework problem, okay, that I have assigned, all right? Okay, so here's the next one, all right? And I know, just hang in there, guys. Hang in there. Be tough, all right? Find the interval of convergence of the series. For what values of x does the series converge absolutely and conditionally, okay? All right, so if we want to check the absolute convergence of it, then this would be sigma n equals 4 to infinity of the absolute value of x minus 2 raised to the n over 3n. Okay, so this becomes sigma n equals 4, and to be the absolute value of the numerator over the absolute value of the denominator, but this denominator will never be negative, okay? So we can just write 3n in the denominator, okay? And then for the top, that's the absolute value of x minus 2 raised to the n, right? But that would be, okay, the same as the absolute value of x minus 2. It's really this base that determines whether it's negative or positive. So we just have to take the absolute value of that. So the absolute value of x minus 2 raised to the n, okay? Now, to do this, okay, we have powers of n, and then we're also multiplying by n. So this would be the ratio test, okay? If this was 3 to the n, then I would be going to looking at geometric series, okay? Because then you could raise the whole thing raised to the n, because both the denominator and numerator would be raised to the n, okay? So slightly different, right? 3 to the n versus 3n, okay? It changes the problem, okay? So for this one, we want to do the ratio test again, okay? So we want to do the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Okay, so now, all right, if you look at this, right, okay, this is going to establish, because we're taking the absolute value, this will establish the open interval in which it's absolutely convergent. And then we're going to have to check the endpoints, okay? All right, so here we go. All right, so this is going to be the limit as n approaches infinity of the absolute value of, and this one's going to be x minus 2 raised to the n plus 1 over 3 times n plus 1 times, and then it's going to be this, we're dividing by a sub n, which is the same as multiplying by the reciprocal, right? So it'd be 3n over x minus 2 to the n. Rearranging the terms here, this would be the limit as n goes to infinity of the absolute value of x minus 2 raised to the n plus 1 over x minus 2 raised to the n times 3n over, and then this would be 3n plus 3. So we're going to have to subtract, these bases are the same, so we're going to subtract the exponents. N plus 1 minus n would just be 1. So that'd be the limit as n approaches infinity of the absolute value of x minus 2 times 3n over 3n plus 3. And if we take the limit as n goes to infinity of this one, it would just give us the absolute value of x minus 2. And this one would give you just 1, right? So times 1. And that's a positive 1, so we don't need the absolute value, okay? So that means this becomes the absolute value of x minus 2, okay? All right, so when do we know this is absolutely convergent? When this is less than 1, right? So absolute value of x minus 2 is less than 1. Okay, we know it's going to be absolutely convergent for this. And then this is going to be, that would mean x minus 2 has to be in between -1 and 1. So -1 less than x minus 2, which is less than 1. And then we're going to add 2 to the left, the middle, and the right. So adding 2 would give us 1 is less than x, which is less than 3. So we know, we've already established that it is absolutely convergent between 1 and 3, okay? But what's happening at the endpoint at 1 and at 3, right? Okay, so we got to establish that, okay? So I'm going to do the next one I'm going to do on the next page, okay? And I'm going to do the endpoint at x equals 1. All right? So I'm going to turn page and I'm ready for this next one, okay? So we're going to check the endpoints. And we're going to check it at x equals 1. Okay. And when we do that, that would be sigma n equals 4 to infinity of, and we're checking at 1, right? So that's going to be 1 minus 2 to the n over 3n. Okay, so 1 minus 2 is -1. So this is going to be -1 to, I forgot the sigma, right? You got to write the sigma. It means something totally different if you don't write the sigma. Okay, so sigma n equals 4 to infinity of -1 to the n over 3n, right? Okay. All right. So now, okay, we're going to check this. This series became this one, right? And now we got to check the convergence of this one. Is this one absolutely convergent or is it conditionally convergent? So let's check the absolute convergence of it first, okay? So sigma n equals 4 to infinity of the absolute value of -1 to the n over 3n. That's equal to sigma n equals 4 to infinity. Now this denominator is always going to be positive because it starts at 4, and this one's going to be positive because we're taking the absolute value of it, so it becomes 1 over 3n. Okay, and again, you can think of this as being 1/3 times 1 over n, and each term of the series would be being multiplied by 1/3, which means you could factor it out and rewrite this whole series, right? So this becomes 1/3 sigma n equals 4 to infinity of 1 over n. What do we know about this series? Well, that's the harmonic series, right? And since it's the harmonic series, we know the harmonic series diverges. So this would have to diverge because this one's the harmonic series, and we're just multiplying the harmonic series by 1/3, okay? All right, so we have 1/3 sigma n equals 4 to infinity of 1 over n. We know that this diverges, but you got to give a reason why, okay? Diverges because sigma n equals 4 to infinity of 1 over n is the harmonic series. which diverges. Okay, so what we've just established is this series, the original series, is not absolutely convergent at x equals 1. So now we're going to check, is it conditionally convergent, right? All right, so we have sigma n equals 4 to infinity of -1 to the n times 1 over 3n. Okay, so this is an alternating series because of this piece right here, and because it's an alternating series, we need to use the alternating series test. This is our a sub n right here, right? So a sub n is equal to 1 over 3n. Okay, and what do we know about 1 over 3n? 1 over 3n is always going to be greater than 0. And 1 over 3 times n plus 1 is going to be less than or equal to 1 over 3n. That's going to be true because 1 over 3n plus 3 is less than or equal to 1 over 3n because this denominator is bigger than this denominator, okay? And then the limit as n approaches infinity of 1 over 3n, yes, that's equal to 0. Okay, so what do we know? We know that the series sigma n equals 4 to infinity of -1 to the n times 1 over 3n converges by the alternating series test, which means our original series is conditionally convergent at x equals 1. Okay, so now we need to do at x equals 3. Okay, all right, so I'm going to turn the page and I'm going to do the next one at x equals 3. Okay, at x equals 3, we have sigma n equals 4 to infinity of, and this time we're going to have 3 minus 2 to the n power over 3n. And this becomes sigma n equals 4 to infinity. And that's 3 minus 2, right? 3 minus 2 would be 1. So that'd be 1 to the n over 3n. Okay. And then, okay, if this is 1 to the n, well, 1 to the n is always going to be 1. So this is sigma n equals 4 to infinity of 1 over 3n, right? Okay. And so, all right, if we check the absolute convergence of this, sigma n equals 4 to infinity of 1 over, absolute value of 1 over 3n, which gives you sigma n equals 4 to infinity of, okay, so this is just going to be 1 over 3n, right? So by doing this, okay, so when we take the absolute value of the terms, right, then that's the same as the original series, right? So we're going to establish whether this is absolutely convergent or it's divergent, okay? Now, what do we know about this? Well, this could be rewritten as sigma n equals 4 to infinity. Oh, well, okay. Let me wipe out this. Okay, I meant to write this as 1 over 3 times 1 over n, right? Which means we can pull the 1 over 3 out because we've seen this series before, right? If you've already tested and you notice this is the same series as earlier in the same problem, you can just refer to that previous test, okay? Okay, so 1 over 3, n equals 4 to infinity of 1 over n. Okay, so you notice this is the harmonic series again, right? So it's 1/3 times the harmonic series, which we know diverges from the previous endpoint. Okay, so we know this diverges, right? So what do we know? Okay, so it's not absolutely convergent, but it gave us the original series, right? So that also means that it's not conditionally convergent. Okay, so what we now know is that this actually the original series, we just say the series. The series. Okay, so if it's not absolutely convergent and it's not if it's not absolutely convergent and it's not conditionally convergent, then it must be divergent, right? So the series is divergent or diverges, okay, at x equals 3. Okay, so back to the information that we had, right? Our radius of convergence was 1. Okay, and that is from the ratio test, right? We have the ratio, or the radius of convergence is 1. All right, from this endpoint at x equals 1, we established that it was conditionally convergent at x equals 1. And from the other endpoint, we said it was divergent at x equals 3. So that means the interval of convergence is 1 to 3. And it's conditionally convergent at 1. So we're going to put a bracket on that because that's a convergence. That's the type of convergence. And then at 3, we said it was divergent. So that should be a parenthesis. Okay. And so it's absolutely convergent on the interval 1 to 3, not including 1 because it was conditionally at 1. So 1 to 3. And then it's conditionally convergent at, and it was x equals 1. There's only one x value. Okay. All right. So that's example number 6. So I know I did a lot of examples with you guys, and I know it took a lot of time to do this. Okay, but I want to explain to you that you want to be able to determine the open interval of convergence using that ratio test. Okay, and then you got to check the endpoints, and then sometimes the endpoints sometimes they are absolutely convergent there, and sometimes they're conditionally convergent. It just depends on the series, right? So some of them we got both endpoints were convergent. And then some of them we got only one endpoint, and then you can also get it where neither of the endpoints are convergent. All right, so all these situations can happen. Okay, so I'm going to turn to my assignment sheet, and I'm going to write down show you what I want you to do, what problems I want you to do out of the book. Okay, so I'm going to go to my assignment sheet now. Okay, so this is going to be assignment 11-8. Okay, and this is going to take you some time. All right, and I know that. What I want you to do is I want you to do page 528, 23, and I want you to do 23 through 31. So I'm going to change this a little bit. Okay, so I want you to do 23 through 31 odd. I don't want you to do 33. Okay, and then I want you to do 35 through 49 odd. Okay, and so I just want you to do these problems. Okay, I'm going to give you about a week to do this. Okay, because I know this is going to take you a long time, and it's also on top of the AP review that I'm doing. Okay. So what I'm going to do is, and I know I put 4/2 here because that's when I had planned on doing it, but really I'm recording this on April 13th. Okay. All right. So what I want you to do is do these problems. Just take your time, do a couple of problems a night. Don't put them off because they're going to be, and, it's just going to be too much to do at once. Okay. So just do a couple problems and it won't be that overwhelming if you just do a couple problems a night. Okay. Plus, you don't have anything else to do, right? Just kidding. All right. Okay. So you guys take care and I'll see you next time.